Alright, so I'm going to do a couple problems from this week's problem set. This is problem 13, which is requested, and it says points A and B lie in a circle centered at O, and angle AOB equals 60 degrees. A second circle is internally tangent to the first and tangent to both OA and OB. What is the ratio of the area of the smaller circle to that of the larger circle? So I did my best to draw this picture. It's kind of tricky to draw freehand, but I figured I would just get it set up here. So this is generally what the picture looks like, and we want the ratio of the area of the smaller circle to the larger. And since we're looking for a ratio here, that basically means that we can make these circles any size we want. So I just went ahead and made the radius of the larger circle 1, and that way at least I get an expression for the area of the larger circle. So the area of the larger circle is pi r squared, which would just be pi. And now we have to go about finding the area of the smaller one if all these conditions are to be in place. So the fact that there was a 60-degree angle there made me think that perhaps I should try drawing an auxiliary line here. Okay, now notice that's that is also a radius of the big circle, so that must be 1. And then I knew that drawing these lines here, for instance, that gives me a right triangle, and by symmetry, this here would be a 30-degree angle. That's 90, making this a 60-degree angle. And so if we zoom in on that, and make that triangle, that right triangle bigger. Couple of things we can do. One thing is we should probably introduce a variable somewhere. So if that's 30 and that's 60, I'm going to call this side opposite the 30x, and that's the radius of the circle. And we'd want that because if we knew that, we would know the area of the smaller circle. So I'm going to call that x, and if that's x, then the hypotenuse is 2x, and this would have to be x root 3. So now if you return to this diagram here, since I'm calling this side here x root 3, this here must be 1 minus x root 3. And although actually now that I think about it, I don't think that's useful. On the other hand, but we'll mark it up anyway. The other thing to notice is that if this side here, which I'm going to put in red, right, that's 2x because that's the hypotenuse there, then this expression here must be 1 minus 2x because the entire line is the radius of the circle. But now I've got two expressions for the radius of this small circle. It's x, and it's also 1 minus 2x. And so setting those equal is going to tell me the radius of the smaller circle. So x equals 1 minus 2x. Solving gives you 3x equals 1, or x equals a third. And so therefore the area of the smaller circle would be pi r squared, which is pi over 9. And so then the ratio that we're looking for would be, so it's the ratio of the smaller circle to the larger, so it would be pi over 9 divided by pi, which reduces to 1/9. So the answer should be B. So someone else had requested problem 23. Now I gotta admit, this problem gave me some pause. It's not one that I immediately knew what to do, and it's very difficult to do if you haven't taken pre-calculus and covered, the trigonometric form of complex numbers. You really have to have some experience with that in order to make sense of this problem. So just kind of disclaimer, this wasn't like an obvious one. I had to stare at it for a while. So it says the solutions of the equation, and then it's an equation in the complex numbers, are the vertices of a convex polygon in the complex plane. What is the area of the polygon? So, generally speaking, one fact that's important to know, and I will just kind of give you a quick, almost like a crash course in some trigonometric forms of complex numbers. If I were to solve the equation x, let's say the equation x to the, well, x squared equals 1, right? Well, we know the answers to that equation is plus or minus 1. So if you were to graph plus or minus 1 in the complex plane, so the complex plane has a real axis and an imaginary, we see that 1 is here and -1 is here. And that doesn't seem like there's anything interesting going on there, but the idea is that the roots of equations, when plotted in the complex plane, are lie on a circle of radius, whatever the distance is from the origin to one of the solutions, and they're evenly spaced. So those are two facts that we need, right? So right, these are clearly evenly spaced. They're 180 degrees apart. Okay, that fact is what we're going to need, because once we find one answer and how spaced apart they are, we're going to see that we'll have both the we'll have the dimensions of this polygon, and we'll essentially know exactly what it is. So I stared at this for a while and wasn't exactly sure how to solve it. One thing finally stuck out at me, and that was, look at the coefficients. They are 1, 4, ignoring the -6, 4, and 1. That should remind you of the fourth row of Pascal's triangle, right? So the fourth row of Pascal's triangle is 1, 4, 6, 4, 1. And at some point, hopefully, you learned about the binomial expansion, which tells you that, for instance, if you were to do x plus y to the fourth, right, the way to do that quickly rather than actually multiplying it out is you can start with x to the fourth, and the next term would be x cubed y to the 1. The next term would be, or include x squared y squared. The next term would include would be x to the 1 y cubed plus x to the 0, which is 1 y to the fourth, and then you go stick in the coefficients 1, 4, 6, 4, 1, and you've successfully expanded it. So we're kind of working in reverse here, because I see it's as though something was expanded. And if you look carefully, it's as though the z is your x and I is your y. So I took a little guess here and said, is this z plus I to the fourth? So I'm going to use the binomial expansion and expand that out. I think I'm going to do it on the next slide, because I feel like I'm running out of room here. So we'll do that on the next cleaner slide. All right, so the claim here is that I think this has something to do with z plus I to the fourth. So let's just check. Let's expand z plus I to the fourth. Well, if we use the pattern, that would be z to the fourth, I to the 0, plus z cubed I to the 1, plus z squared I squared, plus z to the 1 I to the third, finally plus I to the fourth, z to the 0, and then you go stick in your coefficients using Pascal's triangle. So 1, 4, 6, 4, 1. Now if we simplify this, we're going to get almost everything we see up there. So z to the fourth, that's just z to the fourth, which checks. 4z cubed I, that works. That's what we wanted. And then I squared is -1, right? So if you expand this third term, or simplify it rather, you get -6z squared. So far, so good. And I cubed ends up being -I, so this is in fact -4zi if you were to clean it up. And then here's where we finally, our luck kind of runs out. I to the fourth is 1, so we've got a +1 here, right? So that's not what we want up here. So what that tells us is that this is almost, what we see up here is almost z plus I to the fourth, but in order to get what it really is, it's z plus I to the fourth. We have to get rid of this 1, so I'm going to -1, and instead of a 1, I have a -I, so I have to -1 to get rid of this, and then I'm going to minus an I. That is a way of rewriting the equation. And once you've rewritten the equation, we want it to look like this. And here is where you're going to need your pre-calculus, your trigonometric form of complex numbers. So I will solve this equation on the next slide. All right, so we want to solve this equation, z plus I to the fourth equals 1 plus I. So I'm going to do something a little sneaky here, and that is, I don't like the fact that this says z plus I to the fourth. I'd rather it just say z to the fourth or one variable to the fourth. Those are easier to solve. So I'm actually just going to replace, I'm going to let w equal z plus I, where w is my new temporary variable, so that this becomes w to the fourth equals 1 plus I. This is going to be easier to solve. And even though solving for w is not actually the same as solving for z, we do know that once we find w, in order to get z, we just subtract I from w. Now, I actually am not going to have to do that because this problem doesn't ask us to solve the equation. It asks us to find the area of the polygon that's formed by the solutions. Now, the solution set is going to have 4 answers. And so what that tells us is that, once we have our 4 answers, for w, if we wanted to get the answers for z, we would just subtract I. But subtracting I, well, let's just say these are my 4 answers. Right, this is my first answer, W1, W2, W3, W4. If I want to get the z answers, all I'm going to do is subtract I, but that just means shifting down, right? Subtracting I means shifting down by I. And when you do that, you're changing the solutions definitely, but you're not changing the area of that of that quadrilateral. So solving for w and going through this problem as though w is what we care about is actually going to help us. The second thing is, another thing you'll learn when you do trigonometry and pre-calculus, these answers here, w to the fourth equals 1 plus I, they're going to be 4 answers, and they're going to be evenly spaced around a circle of fixed radius. Okay, so here's how we do it. We're gonna replace w with its with a complex form. So I'm going to call it RCIS theta. That's the trigonometric form of a complex number to the fourth. And I'm going to replace 1 plus I with its trigonometric form, which is root 2 CIS 45 degrees. Okay, and this, using de Moivre's theorem, becomes r to the fourth CIS 4 theta equals root 2 CIS 45 degrees. Okay, and then real parts have to match with real parts. Imaginary with real parts match. R values match with R values, and angles or arguments match with arguments. So I have r to the fourth equals root 2, telling me that r is root 2 to the 1/4, which you can rewrite as 2 to the 1/8. Okay, and then if I go ahead and set these equal, I know that 4 theta is equal to 45 degrees plus any coterminal multiple of that. So plus 360n, where n is an integer, dividing by 4 tells us that theta is, I guess I kind of wish I used radians, but it doesn't matter. 45 divided by 4 is what? It's 11.25 degrees. And the distance between the answers is 90. So here's what we need. Here's the insight we need. It looks like our if we were to graph our solutions for W in the plane, like I sort of did above, we know that the first answer is going to be 2 to the 1/8 units from the origin, and we know that its first is going to happen at 11.25 degrees, so let's just say that that's our first answer. The next one is when you add 90 degrees, it's going to be 90 degrees apart, which brings you somewhere over here, but the key idea is that that's a right angle, right? And similarly, when you add the next one, you're going to get you can get the third answer, and then the fourth one will be over here. Okay, those are all right angles. Since the r value is the same, we have a square here. Okay, now this is a pretty sloppy square, but there's my square, and this is my r value, which I've learned is 2 to the 1/8. And from here I know that that would be 2 of those. So this whole distance is 2 to the 1/8, and that'll allow me to get a side because that's a right angle, and the side times root 2, side root 2 is supposed to be 2 times 2 to the 1/8. So I'm running out of room. I'm going to go in the next slide to finish this off. All right, so just to finish up, I know my drawing's a little sloppy here, but really sloppy. Basically, we know that we're dealing with a square. That's the side, that's the side. We found out the diagonal was 2 times 2 to the 1/8, and that means that to get a side length, we know that the side times root 2 is supposed to be that, which means that the side is equal to 2 times 2 to the 1/8 divided by root 2, and so the area of this quadrilateral that we want is side squared, which is 2 squared is 4, 2 to the 1/8 squared is 2 to the 1/2, and root 2 squared is 2, so it's 2 times, sorry, it's not 2 to the 1/2, it's 2 to the 1/4. Fix that up here. 2 to the 1/4. So that's 2 times 2 to the 1/4, which is 2 to the 5/4, which is letter D.